All right, my friends, let's get going here. Let's see how it went. Okay, so getting started on the proof. Remember that with a mathematical induction proof, you always start with the basis step, where you're basically showing what happens if n was 1, and you're hoping that your claim holds true when n equals 1, because if it doesn't, then we're not going to be able to prove it. So sum of the first term, the first partial sum on the term by term side would simply be 1 cubed, which is equal to 1. You can simplify it in your head. And then on this side, if n was a 1, you'd have 1 squared times 1 plus 1 squared over 4. And we're hoping that this equal sign right there is true. Is it? 1 plus 1, 2 squared is 4. Yes, it is true. All right, great. We just passed our basis step, and so just a little ladder map over here. We just got our foot on the first rung of the ladder. All right, one step down, infinity minus 1 left to go. Okay, let's see. Now for our inductive step. Okay, remember there are two pieces to your inductive step. There's your assumption, and then there's the burden of proof piece. So let's get started with the assumption. So we assume that our claim holds true let's see, oops, that, I said that funny, that for, or let's have less writing, that there exists some value, k, from the set of the natural numbers such that our claim holds true for n equaling k. That is, so now let's make sure we're very clear as to what our claim is. Our claim is that the sum of the first k terms for some arbitrary constant k, term by term, would be defined as 1 cubed plus 2 cubed plus 3 cubed, all the way up to, whoops, not n, k cubed. But that is indeed equal to k squared times k plus 1 squared all over 4. All right, so we just showed, or sorry, we're assuming that there's some kth rung of the ladder you can get your foot on. Okay, now, so that's the first part of the inductive step. Okay, now for the hardest part. So now, all we must show is that our claim also holds true for n equaling k plus 1. Okay. All right, let's get started on that. Okay, so sum of the first k plus 1 terms would be 1 cubed plus 2 cubed plus 3 cubed plus all the way up to, you'd still have k cubed, that's the kth term, but then you'd also have the k plus 1 term on there. Okay, now this is not the part we are arguing, okay? The part that we're trying to argue is that the formula, we're trying to argue this side, right? That you can use that little formula instead of doing it term by term. So now let's talk about scratch work off to the side. What is our goal? So this is scratch work, not part of your proof. So our goal is to show that this mess that we've got, oh goodness, okay, of term by term junk, that we can simplify it down and have it equal the sum formula, where instead of n's, you have k plus 1. So that would be k plus 1 squared times, let me use different brackets here, times k plus 1 squared all over 4. So I just took this formula, replaced all the n's with k plus 1s. Now that is pretty unsimplified. So let's show, so this is our ultimate goal right here, but let's show right before we get that, what will it probably look like? So right before that, it would look like k plus 1 squared And then inside here, you'd have k plus 2 squared and then all over 4. So this is what it would look like right before we get it to look like our final goal. All right, so now that we know what we're aiming for, let's see if we can get from here to there. So let's take this term-by-term expansion of the k plus 1 terms and replace the first k terms using our assumption right here. Replace that with k squared times k plus 1 squared over 4. And then bring down that k plus 1 term. There we go. Now let's just follow our algebra nose. Notice what we've got is two fractions that need to be added. And over here in our goal, there's nothing, essentially, we don't have fractions added. So that means we must need to just add these fractions together. So let's just get common denominator. We could multiply the second piece here by 4 over 4. And so we'd have k squared times k plus 1 squared plus 4 times k plus 1 cubed. And that's all over 4. Now let's take a moment and use this little scratch work off to the side, kind of look at where we're at and look at where we want to go, okay? There's a common mistake here, is that students want to expand this top part out all the way and then refactor it. But I want everybody to make sure you notice that the numerator here has a common factor already. Both terms have k plus 1 squared in them. And so instead of expanding it out, we're actually better off in this case just factoring k plus 1 squared out. And so k plus 1 squared would have to be multiplied by k squared to get this first piece back. And then it would have to be distributed into 4 and k plus 1 to get this second piece back. I hope that makes sense. Now look at where we're at and look at where we want to go. We have this expression and we want to get something that looks more like this. And so you can kind of see stuff that you don't want to mess with and keep in stuff that you do, right? So really, I would leave k plus 1 squared just like that. And I now would distribute in the stuff that you have in the parentheses. So k squared plus 4k plus 4 over 4. And then that would equal k plus 1 squared times k plus 2 squared over 4. And I didn't leave myself enough room, so I'll have to go this way. So that would equal, now we're just going to go ahead and like unsimplify it and show that it's equal to this mess. So that would equal k plus 1 squared times k plus 1 squared all over 4. And once you've got there, you've completed your inductive step. So going back to the ladder analogy up here, we just showed that if you can get to the kth step, you can get to the k plus 1 step. You can, and that would mean, whoops, since we also showed that you could get to the first, this loop shows you could get to the second, the third, the fourth, all the way up to the infinite wrong. Okay, our conclusion, don't forget about that part, would be therefore S sub n, which was defined as 1 cubed plus 2 cubed plus 3 cubed, all the way up to the nth term cubed. That could be found by doing n squared multiplied by n plus 1 squared all over 4, and that is indeed true for all n from the natural number set. We did that by mathematical induction. There we go. All right, my friends, one more example just to really pound it in. So for example 5, this will be the most challenging one that we'll do here. If we were in a normal classroom situation, I would have folks do this in groups on my whiteboards and windows. So if you can possibly grab a partner and have them kind of collaborate with you on this one. I like doing a think, pair, share with this one if possible, where you kind of like brainstorm it out on your own for a couple minutes. And then when you're ready, work with a friend on it, put your heads together, see if you can get it. and then see how it goes from there. Okay, so if you can, work with a friend. If you can't, then go ahead and just do example 5 on your own, and then check in with me in the next video, and we'll see how it went.